Hello, Chemistry 12. This is Mr. Chan again. And today what I wanted to do was we wanted to expand a little bit on KSP, or solubility equilibrium expression. Now, last day's notes, recall when we talked about solubility in Chem 11, all we did was we looked at a substance and we looked at the solubility table and saw if it was not soluble or low solubility. Then we expanded that to say, hey, well, how about put some value to it in terms of things like the solubility ion product constant, where we're actually looking at the concentration of the ions from an insoluble solid. Now, if we take that into consideration, where we have to consider the concentration of ions, what happens is we run into a little bit of a problem. So I'm just going to show you a demo here. And I'm going to show you, okay. So what I have is I have Ki, and I have, I don't know if you can see that, PbNO3. Now, if you look at the solubility table, and if we were to mix Ki, as you can see on the test tube on the left, okay, what happens is we get a nice yellow solid precipitate. And looking at the solubility table, you know that the precipitate here would probably be lead iodide. Now, but if I were to do the exact same chemicals, but in this case, I have, before I mix them, I put 1 drop into water, mix it up a little bit, 1 drop in water here, mix it up a little bit. Notice if I did the same thing, there's no precipitate. Okay, so there is no precipitate. So is there a trick up my sleeve? The answer is no. So using KSP, now we know that a precipitate, yes, theoretically should form, but is dependent on the concentration. So it doesn't necessarily always form because the concentration sometimes may not allow it. Okay, so that's what I want to talk about today. And this idea about how precipitation is dependent on concentration is something called trial KSP. Now, so to find out if a precipitate will form or not when 2 solutions are mixed, one needs to calculate a trial KSP or TKSP when the ions, using the ions in the final solution. Now, I've given you 3 scenarios where trial KSP is greater than given KSP. A precipitate forms because the ions exceed that which is allowed. Trial KSP is equal to given KSP. Solution is saturated and reached max concentration of ions. And if trial KSP is less than the given KSP, no precipitation because the ions have not reached its maximum limit. Now, I've given the scenarios of A, B, and C. And what I want to do is I want you to just copy down the 3 scenarios. Okay, so I'm going to pause it here, or you can pause the video here just to copy this down. Now, so what does these 3 situations represent? So situation A is when trial KSP is larger than KSP. So it's like saying you're mixing 2 solutions together and you pour, let's say, into a set volume container. Let's say in this case, 500 mils. So you pour 400 mils of one solution into 300 mils of another solution. You max out on the vessel, and what you get is you get spillage. This is like a precipitation. Okay, that would be like the trial KSP is larger than the given KSP. If we were to look in the scenario here, in my little demo, that would be like here where we have our yellow precipitate. This is the excess ions that the solution cannot hold. Okay? Now, let me just move that there. Okay? Situation B, where the trial KSP is equal to KSP, what happens is that the solution just maxes out on what the vessel can hold. And this is what we call the solution is saturated or just about to precipitate. So this is just filled out. Situation C, where the KSP is larger than the trial KSP, the two volumes do not even fill up the vessel. And so what you have is you have empty space. This is where you have no precipitate. So if we look back in our scenario here, where I had the two beakers here, even though I used the same chemicals, the concentrations were so low that the solution, the resulting mixed solution, had no problems in keeping the ions in solution. And this is why you did not form a precipitate. Okay, so here with the two beakers, that would be like situation C. Here in the test tube, this would be situation A. Now, let me go back here. The analogy I give is, let's say you are going to all you could eat or a dinner. So sometimes you eat so much that your stomach gets full and then you kind of throw up all the extra. That would be like situation A. You've eaten too much for your stomach to hold. Situation B would be like you going and having a dinner and you are just perfectly fine. Okay, you don't want to eat anymore. You are just filled out. Okay, situation C would be like you go for dinner, but what happens is you don't eat enough, and so you are more than able to eat like your dessert or a second meal or a snack or something like that. Okay, now some of you might take a look at this and say, hey, Mr. Chan, this is similar to chemical equilibrium. Right, when we did chemical equilibrium, and we did our KEQ calculations, remember we talked about here a trial KEQ, okay? And here in this case, trial KEQ, notice the similarities. What you have is you have, trial KEQ is equal to KEQ, trial KEQ is greater than KEQ, trial KEQ is less than KEQ. Take a look at the scenario here and see how that is similar to what we have with solubility equilibrium. Okay, but instead of just talking about shift left or shift right, we're talking about whether or not precipitate forms or no precipitate. And we'll talk about that in a few minutes. Now, what I want to do is I want to give you a sample calculation. Okay? It says a solution is prepared by adding 750 mils of 4.0 times 10 to negative 3 molarity cerium nitrate, and you add that to potassium sulfite. Will cerium sulfite precipitate from this solution? Okay, now, the first thing you should always do is you should always write the balanced equation. And you should always try to find out which one will possibly precipitate. Now, so when you write out this double replacement reaction, using the solubility table, you will find out that this substance is the precipitate. Okay? If you use your solubility table, you will find out that cerium sulfate will precipitate. This is from the solubility table. And here, this is soluble. Okay? Now, you might say, well, Mr. Chan, what if it's not on the solubility table? How can we figure it out? The other way to figure it out is you read the question. You have cerium sulfate, and they give you the KSP, precipitate from this solution. So they actually give you the value of KSP for this particular potential solid. So that's another way. So number one is you can check using the solubility table. Number two is you can actually look at the individual question. So what do we do when we calculate trial KSP? So the first thing that we need to do is you need to do dilutions because you are mixing the solutions together and find the concentration of the ions. Now, this goes back to the review that you should have done at the very beginning of solubility, where you either read, depending on which class you're in, whether you read about doing dilutions and finding out the concentration of ions, or you actually watched the video that I put on for regular Chem 12. Okay, so in this case, what you would do is you would go, for your precipitate, so you would have cerium nitrate. Okay, so what you would have is you would have, let's look at the beginning, you have 4.0 times 10 to the negative 3 times 750 over 1050. Okay, and what you would get is you would get a concentration of, let me just calculate this out, 4e negative 3 times 750 divided by 1050. So I would get 2.86 times 10 to the negative 3. Okay? So in this case, the concentration of cerium ions, so this is 3, this is 3, this would be 2.86 times 10 to the negative 3. Okay? Now, you do the same thing for potassium 2 sulfate. Okay, so you do the exact same thing, whatever it is, and you find the concentration of sulfate ions. That would be equal to, if I did that, to negative 2 times I get 5.71 times 10 to the negative 3. Okay, now how did I know just to focus on cerium and sulfate? The reason being is because I figured out in section A which was the precipitate, and those are the ions I should focus on. Now, what is step number 2? You want to calculate the trial KSP using the concentrations. Okay, now you remember from KEQ, when we did trial KEQ, the values were at the initial concentrations. Okay, remember, we plugged in the numbers in the initial concentrations. So that's what we're going to do exactly the same. So here we have cerium sulfate. Is in equilibrium will be 2 cerium plus 3 and 3 SO3 minus 2. Now, if we set this up as our part of our ice tables, okay, we don't have to worry about this one, but the initial concentrations that we have are from the ones that we calculated. So for cerium is 2.86 times 10 to the negative 3. Here would be 5.71 times 10 to the negative 3. Okay? Now, what we do is we use these values to calculate trial KSP. Okay? So, for trial KSP, that is equal to the concentration of, concentration of cerium plus 3 squared, concentration of SO3 minus 2, all cubed. Now, some of you might say, well, Mr. Chan, do I need to double the concentration of cerium because there's a 2 in the coefficient, or triple the sulfate concentration? No, remember, the only time you use the coefficient 2 or 3 is when you are focusing on the change in concentration. Because I am just using the trial KSP and the initial concentrations, I do not need to use the mole ratio, okay? I figure out the concentrations in step number 1, and then in step number 2, just plug the numbers in. So here would be 2.86 times 10 to the negative 3, all squared. You have 5.71 times 10 to the negative 3, all cubed. Let's do y to the 3 times 2.86 e negative 3 squared. So again, an answer of 1.53 times 10 to the negative 12. Now, so what we found in this case is, notice, going back to the original question, my KSP is 1.9 times 10 to the negative 10. So in this particular case, because trial KSP is less than KSP, therefore, no precipitate. Because not enough ions. Okay? All right? And so what that means is you might say, well, Mr. Chan, how does that relate to trial KEQ? Remember when trial KEQ is less than KEQ, you had too much reactant, reaction shifts towards products? Well, what that means is there's not enough ions, so there's no precipitate. So what happens is this equilibrium can shift to the right to form more products. So by shifting to the right, what that means is that more dissolves because you're forming more ions. Okay? So what you could do is when you are looking at this, you can just stop it at this point and just say, oh, no precipitate because not enough ions. But if you were to figure it out, what you could think of going back to equilibrium, the trial KSP is less than the KSP. There's not enough ions. So the equilibrium can shift to the right to produce more ions. Basically, it can dissolve more. All right, folks, that is trial KSP. And what we can do is, yeah, we'll stop it here for today. All right. Thank you very much. Have a good day.